Okay, so we're going to do op amps. This is should be some review for you from 117. We did some op amp labs there. So we're going to be using the same old 741. It's like an old workhorse. This thing was designed like probably 1975. But anyway, it's still useful. It's not necessarily the highest performing. There's some really good op amps out there that can, provide amplification out to the gigahertz frequencies and beyond. But this one, I mean, it's useful for like a lot of instrumentation, and people still use it. I mean, it's an old design, so I mean, if you need like a cheap and dirty op amp, I mean, it's always a good choice. So anyway, we'll first go through the pre-labs, and then we'll go through the SPICE simulations today. And so that's up to step 8. And then next week, we'll do the build. I'll have an analog discovery, and so I'll guide you. So please try to get your analog discoveries. Try to go to the ECS office and pick it up before next week. And also, I'll send out a little message for some of those that don't have it with the link to Digilent, who makes the analog discovery. And you can go to their website and download the software. And it's really easy. It doesn't take a long time to download, and it's free. And that'll allow you to run it. But anyway, what we're going to do is we're going to build inverting amplifier, non-inverting amplifiers. This next one down here is like an instrumentation amplifier, differential amplifier. Then we're going to check the gain of it, the common mode gain and the differential gain. And then we're going to build this little circuit. This would be like an example of maybe an instrumentation circuit or something where you have a differential input. You don't have necessarily a ground reference where you're connecting. And we'll use that for the op amp, and then that. So there's 18 steps. We're going to do the PSpice today. So anybody here who wants to run PSpice, because it's easier for me to direct one of you rather than jump back and forth to the sassafras environment and to the lab instructions. So please, somebody open up the PSpice, and you can run the show, and you'll have your lab halfway written by the time we're done. Okay, and let's see. Somebody else, I think, just joined. I have 16 on here now. Where's that list? I buried it.
Last week's lab is due next Thursday, right? Or is it due tonight?
All yeah, right. Moodle's probably bugging you now.
Yep.
Moodle's probably bugging you, but you have another week before it locks you out. And then after that, you're going to have to send me an email with your lab report and a lame excuse as to why you couldn't get it done. And then when you send it in, like if I've already graded them, I'll take 15 points off. If you get it in before I grade, I won't take points off.
What if we make you laugh?
Say that again.
What if we make you laugh?
Even on the lame excuse?
Yeah, exactly.
Try, but I'll still take 10 points or 15 points off. But you can try. But also, I mean, I'm gonna close this door. I let the dog out and she did her business. I'll most likely grade on Sunday. So even that's a few days later. Okay. Now I need to find that other download from Moodle. Oh, where's Moodle? Okay, so there's some notes. We're skipping lab number 2. It's not even really relevant anymore because this was when we had old oscilloscopes. So the new oscilloscopes, a lot of the things that we were covering in this lab are just covered by math, and the same with the analog discovery. So this one isn't. This is kind of an artifact. Okay, but anyway, there's some notes for lab 3 here. Here's the lab instructions. So we'll open up the notes. Okay, so there's a pre-lab here. There's like 5 questions at the beginning. 1, 2, 3. Yeah, no, there's 4 questions at the beginning, and generally you want to, before you come on these calls, it would be good to do these calculations so you can question me on them, but then also you got a sense of what the lab's going to be about. Okay, so an ideal op amp. We're not going to be building with ideal op amps, but I mean, these are just some properties of op amps. Oh, I guess this is a PDF, so I can't edit that. Okay. So the input impedance is usually very large, much greater than a mega ohm. When used within the specified operating range, I'll talk a little bit more about that. The inputs are plus and minus are the same voltage. So if you have 1 volt here, you've got 1 volt here. Now, when you're going beyond its operating range, like let's say this has a 10 volt supply. So as you get up to maybe 9.5 volts or something like that, it's gonna the voltage at these two is gonna start drifting apart. It won't maintain. So like if you try to drive this thing, like you've got a 10 volt supply and you're trying to drive 15 volts out of the output, it's not going to operate in its ideal form, I guess I'll say. So the power supply voltages limit how much voltage you can get out of this thing. And you can't go all the way, like if it's a 10 volt supply and minus 10 volt supply, you can't go all the way to 10 and minus 10 volts at the output. There's some internal circuitry that I'll show you that kind of limit how far you can go. Okay, so this is an inverting amplifier and this is a non-inverting amplifier. So in the lab, the pre-lab, it says step 1, for the circuit, write an expression for V out, Vn in terms of RA and RB. And then it has you do select resistors. So here, Vn is equal to Vs1. This is a non-inverting. And this Vs1 is the same voltage as Vn1. Okay. So now if we just cover up this op amp and ignore it, if I put my thumb over it, if we look here, we basically have a voltage divider. V out, RB, N, and then RA. And so we can write the voltage at Vn1, which is essentially the same voltage as Vn and Vs1. So these are the same voltage. I'm sorry, to calculate that, we basically use a voltage divider equation. So we can basically say V out is equal to RA divided by RA plus RB. And then we can manipulate that to where V out divided by Vn, which is the same as Vn1, is equal to RB plus RA divided by RA, which is equal to 1 plus RB over RA. So an inverting amplifier, like if you had no resistors there, if you had a 0 resistance here, you'd basically have a gain of 1. It'd be unity gain. It'd be like if you just put like a loop here, it's what we call like a buffer or a voltage follower or something like that. And that's a useful circuit. A lot of times you want to, an op amp has very high input impedance, very low output impedance. So you maybe want to buffer a circuit out here. And so you would use a short there and just have like a unity gain. And that'll present a higher impedance over here and a lower impedance there. And then Rn, the input resistance for the op amp, is basically the input. The input impedance for the circuit is basically the input impedance of the op amp. I mean, this practically, it's, you know, on a lot of op amps today, you're going to see like 10 meg or greater impedance here. So you're not going to have a lot of current flowing this way, and you're not going to have a lot of current flowing this way. So basically, and this resistance is most likely going to be larger than this one here. So I mean, there's like a resistive loop here, but this one's going to dominate it. And so for all practical purposes, Rn of the op amp is the input impedance of the op amp for the non-inverting circuit. Okay. And okay, so it also asks us to design for a gain of 3. So again, this is the gain equation, 1 plus RB divided by RA. So we basically need a ratio of 2 here. So for instance, this could be 2K ohms, this could be 1K ohm, this could be 10K ohms, this could be 5K ohms. So you have a ratio of 2. And then the gain that you're going to get at the output is going to be 1 plus RB/RA. So it's going to be 1 plus 2. So you're going to get gain of 3. Okay, now over here, this is the inverting amplifier. So with this one, the circuit, the output signal, like if you were to put a sine wave in here, the output would be in phase. This one, if you put a signal in here, the output is going to be 180 degrees out of phase. And so that's why we call it inverting. So if the signal here goes positive, at the output, it's going to go negative and vice versa. Okay, so on this one, we've got the positive terminal tied to ground. So this node is essentially at ground. So now we have V out divided by RB connecting to ground, essentially what's the ground, is equal to VS divided by RA. So here's VS2, that's the source 2, divided by RA is equal to minus VO divided by RB. And the way we say minus is because we have current coming in this direction through that resistor, and we have current coming in this direction through this resistor. So now I can manipulate that equation there. These are basically just equations for current. And I can manipulate that to get V out over VN is equal to minus RB over RA. And now my VN, or my input resistance for this circuit is essentially RA, because this node, for all practical purposes, when it's in its operating range, is ground. Now, again, like if you're really pushing it to the limits, that may not, it may not be ground, and then the thing won't be working correctly. But when it's in its operating range, that's essentially a ground. Okay, so that's the input in resistance or impedance of the op amp. Okay, so now here's just a internal circuitry of an LM741. This isn't the best graphic, but anyway, we have a differential amplifier here, and then the output comes over here and gets like a voltage level shift. And then this amplifier and this amplifier are the output stage. Now we have all these other transistors and resistors here, and we have them here and here too. So what these are called current mirrors. These are controlling the amount of current, making sure that this differential amplifier has a steady stream of current. And then it's also biasing and providing current down this leg. And these here as well, these are like active loads. And then these are resistors. Most likely they show them resistors here. Most likely they're implemented with transistors too, that are just always turned on and have a specific resistance between the gates. Okay, but anyway, the point I want to make here is we've got 1, 2, 3 gain stages in this thing, and the rest of this stuff is to bias the circuit. So to make sure you have the proper current and the proper resistive load on the transistors. And what we see too is this is not, the graphics aren't great here, but we've got these little arrows at each one of these junctions. So these are a PN junction, and we're going to be learning much more about these in this classes here. But the point I want to make is you've got 2 pieces of silicon, like an N-type material and a P-type material coming together. And to turn that junction on, you've got to overcome a certain voltage. And so the PN junction voltage is typically in the order of like 0.4 or maybe as high as 0.6 or 0.7 volts. So that's a voltage drop you have here and a voltage drop you have here. So the point being that because of this internal biasing circuitry, you may set this to 10 volts and this to minus 10 volts here, but your output, you're not going to be able to swing all the way up to 10 volts because you've got to, you're going to at least have a 0.6 volt drop here and a 0.6 volt drop here. And when we build it in Spice, I mean, that's kind of what we'll see. In actual practice, when you actually test an op amp, the Spice models are idealized. When you actually test them, we'll see that it's much larger. Like maybe this thing would only go to, if it's minus 10 volts here, the output could only swing to perhaps like maybe 8.8 volts in the negative direction and maybe 9.4 volts in the positive. But we'll test that next week. So that's a 741. This is the gain. So this is fundamentally what op amps are all about. You can probably provide gain. So this thing will provide up to like over 100,000, a gain of 100,000 at 1 hertz. And then like 100 hertz, it starts rolling off. And you think, oh, geez, that's not so great because it only has a bandwidth of 100 hertz. But that's not the way we use them. What we'll do is we'll put in feedback resistors. And then so this is the open loop gain, but we'll set a gain here of, let's say, 3. And so the line will come across here and we'll have bandwidth out to beyond 10 to the 5th, be less, a little bit less than a megahertz. And so that's what the feedback control resistors do, is they'll tamp down this gain, but it gives you a much larger operating bandwidth. And this, by the way, this is pretty modest. Like I was saying earlier, there's op amps out there, amplifiers that you can purchase that will go out to gigahertz, 10 to the 9th, perhaps 10 to the 10th, for, high wireless communication applications and things like that. Okay, now in the analog discovery kits, the 741 is what we use in the class, and I'll be sending those to students who don't have component kits but have an analog discovery. So the OP37 is a device we have in the analog discovery kit, so we can use that one to build amplifiers. They don't have the 741. And this, again, it just shows you the internal circuitry. These are the gain stages here. This is amplifier, this amplifier, output amplifier. So this is output amplifier, usually a low gain, but it drives a lot of current, or relatively high current. But again, you have all these bias, like this symbol here, that's basically saying a current supply. And that's one of those current mirrors that I pointed at earlier. It's very similar. This is a current mirror here. I don't know why they didn't draw it out here, but this circuit here is the classic current mirror. So what it does is it provides a steady current to these 2 transistors that are in the amplifier stage. And then this is just kind of what the internal die looks like. It's not that big, certainly. It's, probably a millimeter by a half a millimeter. These are just some specifications for the OP37 device. This is a much better device. One of the things we're going to do compared to the 741, one of the things we're going to do is we're going to test the input offset voltage. And so this is microvolts. The max might be 100 microvolts, which would be 1.1 millivolt. Whereas on the older device, the 741, the output offset voltage is going to be in the order of 3 millivolts or less. So this is just a more modern device. It's more refined. So this one here, it says the input resistance is 4 mega ohms. So again, it's generally higher than the resistors used to bias it. Let's see. Input resistance, common mode input voltage range. I don't fully understand this, but apparently for a common mode signal, this thing provides 2 giga ohms of input resistance, whereas this 4 mega ohms applies to a differential input signal. So the common mode rejection ratio, this is a pretty key parameter for these devices. These amplifiers are designed to transmit differential signals and attenuate common mode signals. So this is usually a pretty good figure or characteristic that people use to choose their amplifiers. You want a high common mode rejection ratio, and I think I have a diagram a little bit later. Yeah, okay, that'll describe that a little bit more. Rejection ratio, that's basically it. Gain bandwidth product. So we saw that curve before, the LM741. Its gain bandwidth product was like barely a megahertz. This one, it goes out to, it looks like 63 megahertz. So like if we had like a gain of 3, we could use this thing beyond like in the tens of megahertzes. And then after that, we'd start seeing some distortion. Okay, so here's just an example of common mode and why we don't like it. So for most communications, we transmit on a differential mode. And we transmit, most cables like USB, Ethernet, even coax, I guess you could say. But most communication cables like HDMI and so forth, they use a differential wire. So they twist these wires together, and one is like has the signal is going positive, negative, differentially. It doesn't have a ground reference. And so these red and blue lines represent the currents flowing through. So if you remember, like from physics or perhaps your electromagnetics classes, the right-hand rule, you point your thumb in the direction of the arrow of your right hand, and then you curl your fingers. So when current is going in this direction, the electromagnetic field is curling around in this direction. When the current is going in this direction, it curls in this fashion. So why we do that is so that the electromagnetic fields generated by these currents flowing through the cable, that they cancel each other, and that reduces radiated emissions. So you're not, when you're transmitting on your Ethernet cable or your USB cable, you're not generating a lot of noise just from those high frequency RF signals flowing through the cable. The currents or the electromagnetic fields of the currents cancel. And that's because we transmit differentially. Now there can be common mode. So I drew these arrows going in the same direction. And common mode means that when I've got a current going in this one, like when this is +1 volts, this is +1 volts. And so the signals are going in the same direction. And in that case, the electromagnetic fields combine and they create noise that's radiated out. So like you may have been like, I don't know, there was early electronics. I don't even know if you've experienced it, but early electronics, like you'd be on a cell phone or something like that, or just a wireless phone, and you'd get next to something and it'd be fuzzy. You have static on the line because there was radiated emission. So I mean, a lot of communication circuits, a lot of the challenge of communications, building communication circuits is just minimizing noise, and then also making your circuit robust against noise. So yeah, if you have common mode signals coming down the cable, they can create radiated noise. Now, if there's a noise source nearby, like maybe a motor that's pulling a lot of current that's generating noise, and that electromagnetic field hits these cables, it'll stimulate both the same, with the same amount of energy, essentially. And so you that's another way you get common mode signals on the cable. Or sometimes if there's an imbalance in the circuit, you can develop common mode signals in the cable. So with our amplifiers, we want to not put any common mode out on the cable. We want to just put differential signals. And then at the receiver, if there's noise that was picked up by the cable, we want it to reject that. So we want to have it dissipate that common mode and not pass it through. We just want differential signals coming through the two amplifiers. There was later in the lab when we build, there's a differential amplifier we'll make. And so essentially to set the gain, it's basically these ratios, R6 divided by R4, R5 divided by R3. So if you want your amplifier to have a gain of 10, you'd make this 10K, 10K, 1K, 1K. And then when we go to test, if you want to test differentially, you can take one of these lines and connect it to ground, stimulate this one. If you want to test common mode, how it rejects it, you can tie these two inputs together, drive it with a voltage signal source, and then measure the signal output. And we'll do that next week when we build the circuit. And these are just like notes of when we built it. These are useful. This is basically an inverting amplifier diagram. And this is like the last step of the lab where you put it through that diode circuit. So that's what the output should look like. So we'll revisit this next week. Okay, so that's just the pre-lab notes that are on Moodle. We went through those real quick. So I want to hand this over to somebody who can go and do the simulations for us. Who's going to volunteer to run the PSpice for us today? It's going to be pretty simple. We'll knock that out probably in at least in a half hour. Anybody volunteer?
Else wants to do it, I could do it.
Okay, who's spoke up?
Me, Amer.
Okay, you guys are letting Amir have all the fun, man. Okay, I'm gonna stop sharing. Oops. Get that down. Okay, stop share. And then I'm gonna hand it over to Amir. That's quite a picture, Amir.
Thank you.
That's the one on your driver's license. Okay. Okay, anybody need a review? Well, we're gonna get a review right now of how to get into PSpice. So you go up to like file, new project.
Oh, I was just checking if my recording was still going.
Oh, okay. Oh yeah, and also let's see. I think it was looking for an old file. I think you have to go new project.
New
I have
project? Okay.
I have an icon on top of mine, so I can't see your that corner. Okay, so let's call this lab. Technically, we'll call it lab 2. Yeah. Okay, good. And I just okay. It's coming. Okay, and then over there, I gotta move my picture here. Yeah, that one. Yes, the one that says L3. Yeah, schematics, page 1. And good, we got that. Okay, so first we'll build the inverting amplifier. Okay, so let's just go to and search and then type in LM741. Okay. Okay, so don't use the first one. I did this yesterday and at school. Yeah, that's a better model. The first one was problematic. Okay, good. So now we need 2 resistors. I want just a basic resistor. Those are chip inductors. Let's see.
Just fine.
Go click that icon in the corner underneath that arrow that is a component with a plus on it. Click that. Okay, type R up there. Okay, there you go. Okay, so put them up above. Yeah.
Oh, right here?
That's a good spot. Okay, and that's good. Okay, and then we're gonna need 3 batteries. So type in VDC. Okay, so let's put 2 of them vertical on top of each other to the right in front of the op amp. Yeah, let's put one there and put one. Yeah, go up a little bit higher. Yeah, that's a good spot. Okay, and then let's put one to the left.
Oh, one more. All right.
That'll be our source. We're gonna start it in step number. We're doing step number 5 right now, so we're gonna do a DC sweep of this first. Okay, so let's hook this up, get some wire going here. So first we'll do the batteries. So let's go from the minus terminal of V2 to the plus terminal of V1. Oh, that's good. No, actually, that's good. No, let's disconnect that. That's not ready for that yet. Let's just go to V2 and V1 and put a vertical wire. Yes. Okay. Now the bottom of V1 goes to pin number 4. The top of V2 goes to pin, yeah, that 1, 7, good. And then the output, we can just leave that right now, I think. Okay, So now on the inverting one, we're gonna have the signal come into that one. So let's put that to V3. It's
so-
gonna go to the positive terminal. Yeah, this is the non-inverting amplifier. And then the junction, let's put a wire between R1 and R2. Yeah, that goes to pin 2.
Right here.
Yes. And then the output of R2 goes to pin 6. Yes. And then, okay, so now we got to hook some grounds up. Okay, so R1, the backside of R1 goes to ground. And the bottom of V3 goes to ground. Yep. Good. And then we'll make all those power supplies 10 volts for now. You can move things around if you want to shift
Yeah.
them. Okay, good. So I think we're looking pretty good. Oh, do you want to open up a Word document so you can paste this? Oh, we do need one more ground. In between V2 and V1, we need to put a ground. Yeah, that's what works. Either way works. You can come either way.
Yeah. There.
Yeah, that's good.
There.
Okay.
I'll open up a Word doc real quick.
Yeah, open one up. I'm gonna turn on the lights here. So while we're doing this, man, the rest of you guys, you're letting Amir have all the fun. Next week, well, I guess next week we'll be building, but we'll every lab. I mean, I think every lab from now on is going to be like 2 weeks, and the first week we'll generally do simulations before we build.
Was this a non-inverting op amp?
This is the non-inverting op
Alright.
amp. We're on step 5 right now. So we're going to perform a DC sweep. Okay, so let's go up to piece. Oh, you got that still. Yeah, that one, DC sweep. And our source is going to be V3. So over there to the right where it says name, V3. And we'll start at minus 10 volts down where it says start value, minus 10 to plus 10. And we can do like 0.1 volt increments. Okay. So we can apply okay and run that. It's going to pop up at the bottom. Okay. So now we're going to add traces. Add trace. Let's get rid of the currents. Okay, so we're going to use U1 out. Do you see U1 out? And then we'll do V3 plus. Right there, yeah. Let's see what that looks like. Okay, so there's your output. So the red is going from minus 10 to plus 10. That's your VN. And then the green is your V out. So like, let's put a cursor on there. Trace, and then a little bit ways down, cursor. Okay, and then just click, it'll come to you. And let's put the vertical like around 1 volt. 1 plus 1 volt. Yeah, like right there. Yeah. Okay, so in the bottom window, I've got to move mine. It says that we have 1 volt in and 2 volts. Hold on, I'm confused. We didn't assign our voltages. I'm sorry, we didn't do our resistors. Yeah. So let's make R2 equal to 2K. So that way we'll get a gain of 3. Okay. Let's run that again.
Dated picture.
Yeah, sure. U1 out and V3 plus. There we go. Okay, let's put that cursor back in, trace. Good. Okay, and put it around 1 volt. So what that's telling us is that when you have 1 volt in, you got 3 volts out. So that's a gain of 3. And then what you see happening there, that green line, it flattens out, or we would call saturates when you're at around probably about not quite 3 volts. Or no, a little bit above 3, like around 3.3 probably. Because basically 3.3 times 9 is essentially 10 volts. And then, you can't drive it any higher than that because the supplies limit you. Yeah, capture all that. Okay.
Oh yeah, it's exactly 3.3.
Yeah. Okay, so for kicks, it's not part of the lab, but I'm gonna have you put in a sinusoid right now. Let's go back
Alright.
back and just do that. We'll run a transient real quick. So let's that 10 volts, yeah, get rid of that. Let's put in a V sign. VSIN. Yeah, that's the one. Yeah. Okay, and we'll just do like 1 kilohertz, 0 offset. 0 offset, 1 volt. And 1 kilohertz and AC equals 0. I don't think you have to write hertz. In fact, let's just write 1K.
Okay.
Sometimes it's funky about that stuff. It gets hung up. Okay, so now we'll set up a transient, edit simulation profile, DC sweep, go to transient time domain. So we have a 1 kilohertz signal. So 1 over 1 kilohertz is 1 millisecond. So if we want to see 5 signals, let's put in 5 milliseconds. Okay, and then, oh, hold on. Minimum step size, we'll make that 1 microsecond. 1 U. Okay, now we can go. Okay, let's run that.
Same stuff.
Yes,
U1 out, V3 plus.
Yeah, same stuff, yes. Okay, so the red is your input, and then the yellow, or the green rather, is your output. So it's 3x. So you can see the red ones peak at 1 volt and the output peaks, and they're in phase. Okay, so yeah, why don't you capture that? The reason I'm doing this is we'll be doing this in the lab next week. So you just kind of previews what you're going to be seeing on the oscilloscope. And then you capture that little window in the bottom. And just one other little thing here. Let's see. Pin 3. So these, yeah, it says it's biased at 0 volts. I guess that's okay. Yeah. And then that node between, and pin 2 is at 19 microvolts. So they're essentially the same. So they're not exactly the same, but they're the same within like 20 microvolts. Okay, so you captured that?
Yeah.
Okay, so let's make this into an inverting amplifier now. So now what we want to do is on the very far left, let's break that line. Yeah, let's break that guy. Okay, and now V3 is actually going to feed into R1. So break that line there. Yes. And yeah, now let's connect V3 to R1. That's good. And then pin 3 is actually going to ground. And I think we're good. So let's just run the transient again while we have it set up. Same ones, yep. Okay, so what you see here is it's 180 degrees out of phase. So it's an inverting amplifier. And where you have 1 volt in the input, you got 2 volts at the output. So this one, it only has a gain of RB divided by RA, which is 2 in our case. So yeah, why don't you capture that?
And this is part of what step?
This, we are now on step number 6, I believe. Yeah, step 6. And then step 7 is pretty easy. We'll do the DC sweep too. That's part of step 6. And then step 7, we'll do a modification of the DC sweep. And then step 8 is really just a question. Okay. So did you get all that in your Word?
Yeah.
Okay. Let's go back to our schematic. And we'll put go back and do the DC sweep. So let's get rid of V3 and put a battery back in there. VDC, yep. Okay, and let's give it 10 volts, yeah. Okay, now let's go back and set up the DC sweep. V3, it looks like it's all set up and ready to go. Okay. Same ones. Okay, so here, the red is the input, green's output. So when it goes up in the input, it goes down at the output. And then when it's negative voltage, it goes positive. So let's put a cursor. Yeah, let's put the cursor on there and let's just look at 1 volt. 1 volt, maybe to the right a little bit more. Is that 1 volt? Let's see. No, you're at, yeah, keep going to where
Right. Oh yeah, it's right.
you can even put at 2 if you want. Yeah. Okay, so you got 1 volt in. It's not exactly a 1 volt, but anyway, you got like 1 volt in and you got 1.99 out. So you basically have a gain of 2. So yeah, you want to capture that. And then you can see too on the green where it's limiting. Now, Spice just shows like a little bit of like maybe it doesn't make it all the way 10 volts. It kind of saturates like at maybe 9.8 or but in actual, what we'll see next week when we test that, we'll see that it's actually much larger. It'll like saturate at 9.2 maybe in the positive direction and like 8.8 in the negative. Okay, good. So we just did step 6. So now step 7, what they want us to do is to make a plot for the input resistance. So we're going to plot, they call the input on this circuit VS2, and then the input through the resistor is IS2. So we can get rid of those down at the bottom, get rid of the, no, you're good. We'll keep the circuit. We can just keep it here. We don't even have to rerun. Just, yeah, get rid of those 2 guys. Just press, I think you can just press delete, highlight them and press delete, or there's even a button I think that says delete. Yeah, good. Okay, so now let's put in a trace, and we're going to add trace, and it's going to be, hold on, let me think for a moment. It is going to be V3 plus, and then go to the math function over there. There's a slash, and then let's put in, let's turn on the currents. Turn on the currents because we're on V over I. We're checking the resistance. And let's just put in IR1 and see what that looks like. That's the first resistor. Yeah.
This one or
Yeah,
this one?
Yeah. That's either one I think would work. Let's try that one, see what it looks like. Okay. So this is a kind of odd looking picture. So let me explain it to you. So if you look at the scale on the left, we flatline in the middle, like at around 1K. So that's your resistance. What we're applying here, if you look at that again at the bottom corner there, it's V3 plus divided by IR1. So it's the input voltage divided by the current going through the input resistor. And so that's basically the input impedance of the amplifier. But now we see that when we get to plus or minus 5 volts, it's got that slope. And that's basically saying that we're in the non-linear region there. So because like it's got a gain of 2, so it's trying to push the output beyond 10 volts. So that's what those two like 45 or 30-degree slopes are in either end. The real information here is between -5 volts and +5 volts on the horizontal axis. And again, we have a resistance there of 1K ohm. And then you see that little dive in the bottom, or that's some Spice trying to do math around 0. So that's just kind of an anomaly of the calculation in the computer. If we made it like we did like a 0.1 step size, if we made it 0.001, that spike in the middle would be even smaller. But no, we're all good. So this is basically the simulation of the input resistance of the inverting amplifier. And so it basically shows you that it's 1K ohm, which is R1 in your case. So let's capture that and put that in your report. And that's basically it for today. In step 8, it's basically a question. In step 8, it says, consider the plots of step 5 and step 6. Those are the DC sweeps. Are V out max and V out min the same in both circuits? So what we see is that it tops out and saturates like at 9.8 and -9.8. So in our case, yes, it was. And then it says, consider the assumption of Vn equals Vp. Does the assumption hold when the output is saturated? And the answer is no. Again, next week we'll build the circuits and we'll test them, and we'll see that as we try to drive the output beyond like 9.2 volts, that the voltages at the plus and minus inputs of the op amp will start to separate. And then it's basically, it's not behaving as a linear device. It's just has a mind of its own at that point. Okay. That's basically it for today. Next week we'll build. Any questions? Let me look at my chat, see if there's any new chats that came in. Here we got a chat. Okay, that's Amir telling me that he's going to step up and do the Spice.
The
Okay.
spice must flow.
Yeah, the Spice must flow. Who just said that? Garrett?
Yep.
Okay, for making that lame joke, you get to simulate the next time. Okay. So everybody remember that. Garrett's going to run the simulation 2 weeks from now. Yeah, thank you, Amir, for driving the plane for us again. Okay, I think we're
Thanks for
basically
walking.
done. Any other questions? Lab reports, yeah. So after we finish, so this one we're gonna finish next week, and it'll be due. Spice will bug you the following week, and then it'll lock you out 2 weeks from when we finish. Anything else? Are we done? I think we might be done.
Thanks, Professor.
Okay, thank you. Thanks, everyone. Have a good evening. And I'll be sending out little component kits, and I'll send that list and I'll copy all of you, so you'll have it too. And you can go in this week, contact Jessica, she's in the ECS office, and ask her for a kit to take home. Okay, thank you, everybody.
Thanks, Professor.